welcome to, I think this is Thursday's video about Newton's first law and how we can draw what's called free body diagrams. Before we get into the new stuff, let's review some of the old stuff. So, just a quick 2-minute recap. Remember, forces are any kinds of pushes or pulls on an object. All forces have strength and direction. We can describe forces as being unbalanced or balanced. The difference is that unbalanced forces can cause motion, balanced forces do not. A little bit more detail about that. Unbalanced forces can cause an object that's at rest to go into motion, or it can cause an object that's in motion to change its motion. And also with balanced forces, we have to remember that they are equal but opposite, right? So they cancel each other out. Ultimately, that's what's causing no motion. That is all related to this big idea that's called Newton's first law of motion, right? That an object will stay at rest or it will stay in motion if it's in motion unless it's acted upon by an unbalanced force. Okay, that's Newton's first law. Previously, we had used what's called system schema to help describe how objects are interacting and what forces are resulting. But since we really care about causing or not causing motion, we want a diagram that more conclusively says that, right? So we're going to be using what's called free body diagrams to help us better determine if an object is going to be in motion or not because of the forces that are at work. So what exactly are free body diagrams? This is an example of one. It's really simple. There's just boxes and arrows with labels to help us show the sizes and directions of all the forces acting on an object in any given situation. Now, again, you might be asking yourself, what's the difference between system schema and free body diagrams again? The system schema are used to just brainstorm. What are all the objects that are in the scenario? How are they interacting with each other? What are the forces that are resulting? And we use, dotted lines or solid lines to help kind of differentiate contact versus non-contact forces and things like that. Free body diagrams are a little bit more what I would say calculated. They use just a simple box to represent the primary object of focus. We use arrows to represent the forces, but the direction of the arrow matters and the size of the arrow matters because, as we know, forces have strength and direction, so that's going to come into play with the free body diagrams. Like I mentioned before, free body diagrams are definitely more helpful in helping us to figure out if this object of focus is going to be in motion or not. You can probably already kind of guess, this blue box here isn't going to be pushed one way or the other simply by comparing the sizes of the arrows. Who cancels out with who's larger than who, and whatnot, compared to something like a system schema where you're just this is a weird kind of blah, blah, blah map, and it's just, So free body diagrams, they're definitely going to help us with net force stuff. So how do we draw a free body diagram? There's a couple of steps that we need to do, but the big idea, the big rule that you have to remember is that you have to include all of the forces that exist on our object of focus, all right? If you don't have all of the forces acting on an object, you're not going to get an accurate representation of the scenario, and you might get a wrong prediction about whether it's going to be in motion or not. So, the steps that you need to take. The first one is you draw a box. That should be pretty easy. The box is going to represent the object of focus in your scenario. After that, then you determine all the types of forces that are present just on that object. You draw arrows for each of those forces and you label them according to the type of force. You have to be careful about the direction that they are going, as well as the size. So we will use larger arrows to represent larger forces, smaller arrows to represent smaller or weaker forces. Then we just have to double check ourselves. Is our free body diagram matching what we know to be happening in real life? So let's get into some examples. Here's the first one, classic forces example. A book is at rest on a tabletop. So the first thing that we ask ourselves is, what forces do we think are present on that book? Is gravity pulling the book down? Yes. Is there a spring involved? No. Is there a rope, cable, or anything like that? No. Is there a normal force, or is there a supporting force that helps to push that book back up? Yes. Is there friction? negligible amounts of static friction, but we just don't count it. And since it's not free falling or anything like that, it's not flying through the air, there's no air resistance. So, which forces are present? There's only gravity and the normal or support force. All right, I'm going to delete this one. In the next one, we're going to look at drawing a system schema. So, the objects that we have in this scenario, we have the book, and we have the table, and as always with system schema, we need to include one for the earth. Since the object of focus is the book, I'm going to put a dotted line around it. And then we ask ourselves, okay, what are the different forces we said? There's gravity, and there's the normal force. So where are those forces coming into play? Between what objects? So between the earth and the book, there is, you know what? I did that wrong, because gravity is a non-contact, so that needs to be a dotted line. There we go. So there's gravity there. There's also gravity between the table and the earth. Okay, so then where is the normal force coming in? Who is supporting who? The table is supporting the book. So this is going to be labeled as F sub norm, or the normal force. Okay, so there's our system schema. Now from here, when you think about how am I going to be doing my free body diagram, look at your object of focus and say, what are the lines that are coming off of that main object? And the only forces that we have are the normal force and the force of gravity. So in my free body diagram, I'm going to have two arrows, one of them for the normal force and one of them for the force of gravity. Let me delete this. Whoop. I don't know why that doesn't work all the time. There it goes. And let's go and do the free body diagram. So like the steps were mentioned before, the first thing that we have to do is we draw a box. This is going to represent our book that is sitting on the table. And we said that the two forces that are coming into play just on this book include the force of gravity and the normal force. So you think to yourself, okay, which direction does the force of gravity go? Well, gravity pulls down on a book. So we're going to use the down arrow like this, and we're going to label it F sub grav. Remember, the normal force is the thing that is supporting the book. And the normal force acts in the opposite direction of gravity. And so in this case, we're going to draw an arrow that is of equal length, do the best that you can, about equal length, opposite direction from the force of gravity, and we're going to label it F sub norm, or the normal force. All right. Now, this book, this is where we just double check, is what we drew similar to what we're actually observing in the scenario. Because the forces on this book are equal and opposite, they cancel each other out, so we should see no motion. So is that what we're seeing in this scenario here? Yeah, so our free body diagram is probably pretty good. Erase that, erase that. Awesome, let's go on to another problem. This one says, you push a book to the right in order to move it across a desk. It says, consider frictional forces, which means we are going to include them. But it says neglect air resistance, which means we are not going to include air resistance. Even though it's there, it is so incredibly small. It's as if it's not there. So what forces are present? Do we have gravity? Yes. Do we have a spring force? There's no spring, so no spring force. No ropes, wires, cables, leashes, so no tension force. If there's gravity and there's contact, there's probably a normal force. It said to consider friction, so we'll include it, but we're not going to include air resistance. So, three forces that we need to be including in our diagrams. Let's go ahead and jump to that. Gravity, normal, and friction. Let's start with the system schema just to get our brains wrapped around who's interacting with who. So we have the book, you have the table, you also have your hand, that jumped a little bit. And of course, as always, you should have the earth included. Now again, the book is our object of focus here. We're really focusing on what forces are around that book. So, easy to start with gravity, right? If the earth is there, there's going to be gravity. So it's a dotted line because it's a non-contact force. Force sub grav. And there is also gravity, with the table. So we can put that in there if we want. If you didn't include it, I wouldn't mark you down. Gravity is kind of a, it's an omni, whatever, it's always there. But then, I always tell you that if you see the force of gravity and there's contact between objects, that there's probably the normal force. So who is going to be connected by the normal force? Well, if the book is on the table is supporting the book. So the normal force is a solid line, it's contact, and it's between the book and the table. So that's F sub norm. Now, we said that there was at least one other force from that checklist, and it was the force of friction. Now, because the book is in contact with the table, right, the book is what's sliding across the table, the force of friction is between the book and the table. Since there's contact, it's a solid line, and we label that the force of friction. We included the hand in our system schema because the hand is technically touching the book. Now, since the hand is from a person and the person is pushing the book, hopefully you remember that that is called the applied force. That is F sub app, the applied force. All right, so looking again, when you go from system schema to free body diagrams, you look at that object of focus and you say, what are all the lines that are kind of attached to that object? So in this case, when we have our box in our free body diagram, and that's the book, we're going to have to figure out where are the arrows going to be pointing and how big do they need to be for the applied force, the normal force, the force of friction, and the force of gravity. So let's take all of those ideas and let's go to the next one where we deal with the free body diagram. So again, you start with the box. And there were 4 forces that we had. The easiest ones to start with are the force of gravity and the normal force because they're equal and they're opposite, pretty much always and forever. So gravity is pulling down on the book, so we're going to put a down arrow here and label it the force of gravity. Normal force acts in the opposite direction from gravity and it's about the same amount, so do the best that you can to make them about equal. That's F sub norm. Then we have the 2 other forces. We have an applied force from the hand pushing the book, and we have the force of friction, which is acting in the opposite direction of motion. So where are we going to put the arrows for those? Well, go back to the problem. It says you push a book to the right. Okay, so that applied force is going towards the right-hand side. The applied force is this way. The force of friction acts opposite to motion. So if the motion is to the right, the force of friction goes to the left. Now before you draw that arrow, you need to consider, is the applied force greater than the force of friction? Because if so, then the book is actually able to move. So in this case, since the book is moving, the force of friction is smaller than the applied force. Let's see if I can make that just a little bit clearer in my drawing. I want this to be a bigger arrow than this one. This is the force of friction. Okay, so this is what I'm talking about. If the arrows are the same size, they cancel each other out. We have what's called balanced forces. If one force is bigger than the other force, we draw the arrow bigger, and that's where we get unbalanced forces. And that's how we start to kind of imagine that there's actual movement or motion happening. So in this case, the applied force is bigger than the force of friction. That's why we see the book move to the right. Okay, this is your intro to these slides. I'm going to make a second video that goes over two more scenarios. You can watch it, or if you want to try it on your own and then check your answers, you can do that too. Otherwise, make sure you copy down some of this information into your slides.